question is search in almost sorted array. The difficulty of this question is medium. As we have given the sorted integer array consisting distinct element, where some element of the array are moved either of the adjacent positions. Either that is array may be present array of I may be present at array of I minus 1 or array of I plus 1. Given an integer target, you have to return the index, zero base index of the target in the array. If target is not present, then return minus 1. So let's see what does this mean. Suppose if this is given, let's say 40 is the given, so this its correct position can be this or this. Only this and this can be its correct position, means array of I minus 1 then array of I plus 1. So if we shuffle this position, it will 40 will get its original position. Let's say 10, 10, 3, 20, 40, 50, 70. So here it is the original position of the 40. So that lines means array of I presents only on the two position, means three position, on the original position itself, either on the array of I minus 1, array of I plus 1. See, in this given example, so target is 40 here, so index 0, 1, 2, so 2. Here the target is 90, here target is not present, so returning minus 1. Yes, here target is minus 20, and in the array minus 20 is present, we are returning the index 0. The time complexity is required is log n. If we are searching something and time complexity required is log n, so obviously it is the problem of the binary search. So we are going to solve this problem using binary search, and space complexity is big of what are the topic tags? Binary search, sorting, as I said earlier. Then what can be the very brute force approach for this? Obviously the brute force approach will be for this problem is a linear search. We will traverse the array and simultaneously check with the uh, each element if our element exists or not, and then accordingly we will return the index. Now the traversal start from here, target equal to 40 is not equal, return 2. So this is very simple approach. It has the time complexity of big of n and space complexity of big of 1. Let's see the code and run it. This code runs very perfectly and having the time complexity of big of n and space complexity big of 1. Now let's see the another approach of this problem. As we have said, we are given that problem should be solved by the binary search. So we will try this problem by using the binary search. So we know the typical binary search where we take one low, one high, and recursively, or we can say in the while loop, we calculate the mid, and we check the mid is that our element or not, and according to the value of that element, we uh, change the value of low or high. This is the whole idea behind the binary search. Now let's see here one catch. In this problem, there is array given, but it is not said that it is the completely sorted array. It is the nearly sorted array. So we can't means if you if you know the binary search, there the prerequisite for the binary search. If you have to apply binary search, you need the sorted array first. So it is not the sorted array. So in the better solution, we can do one thing. We will first sort the given array. First sort the no. We will first preserve their original index in the map. Store the original index. Store original index in the map. After that, after storing the original index, we will sort the array. After that, apply the binary search, and then return index from map. So this will be the approach for the this this will be the approach for better, and first we will store the first we will store the index in the map. What is the original index? Then we will sort the entire array for applying the binary search. Then we will apply the binary search, and as we have to return the index of the element if it presents or not, then we will return the original index if present in the array. So let's see the code. So this is the code. As you can see in the picture here, we are storing the all original index in the map. After that, here we sort the array. We sort the array, and all we know how to apply the binary search on the sorted array. Sorted array. It is a very typical template for the sorting the searching using binary search. Here the only things which change is this. While returning, we are returning map of array of mid, means we are returning the index from the map itself, means we have to return the original index for that element. So we are returning index from the map. Now discuss what the time complexity will be for it. Time complexity for it will be, as we doing the operations on the map, so according to the language it will be the big of 1 or big of log n plus plus sorting big of log n, and for binary search big of log n. For searching it is n log n. And time complexity will be big of n, as we are using the map to store the elements. So this will be the time complexity, and this will be the space complexity. Space complexity. Now let's run the code. We are going to return the index from map. This is the only change, and let's run this code. Yes, it is working very fine. And now let's come to our very optimal and final approach, that is the binary search, which takes the time complexity of big of n log n, space complexity of big of 1, constant space complexity. Now how will we do it? Let's see in the blackboard first. Let's take this example itself. So let's to apply the binary search. Here we are, here only one modified thing in the binary search, as we have said that array of I will be present at array of I minus 1 or array of I plus 1. Here only two position will be there, array of I minus 1 and array of I plus 1. So in the binary search, when we check the position at array of mid, we will check on these two positions also. Means if the array is present there, so means if suppose, let's see by the example. If our mid is here, if our low is here, if our high is here, and our target is 40, and our mid comes here, so if the 40 lies somewhere around mid, means if we are here, so we are gonna check this index as well as this index on as well. Every time what we do, we only check mid and then we move on by changing low or high. But this time, as we have said, we are given that the array means elements original position can be the array of I minus 1 or I plus 1. So we'll check both the positions, this will also and this will also. If found, then we will return that particular index, or otherwise we will directly change it low or high. Let's see how to do it. Let's take the code here. This is the code. What will we do is, this is the low, this is the high. Our target is 40. Our target is 40. Then we come here. Our mid is this. Then we check this, not equal. Then we check. Then we check. First we check mid. Then we check. Then we check array of mid minus one. The, then we check array of mid plus one. So this is not equal. Then we check the array of mid minus one. This is equal. So we are returning the array of mid minus one. So this is the case. Now let's say our target is 80. What will we do when our target is not found in the one go? Our target is 80. Our target is 80. Our mid is this now. Is low, high, and mid. So first we will check the 80 with the this 20. So this is not equal. Then we will check the array of mid plus 1. This is also not equal. Then we will check the array of mid minus 1. So this is not equal this time. So what will we do? If array of mid is greater than target, so this is the two steps of the typical binary search. If the array of mid is greater than target, is this greater than target? No, it is less than target. So it is less. It is actually less than target. So we are going to find our element or our target after this, because it is almost sorted. It can be here or here. It is telling the position of the 80 will be absolutely after this, because we have checked the array of I minus 1 or array of I plus 1. So it will be after here. So we are changing it to low plus mid plus 1. So after doing that, low comes here and mid comes here. And by doing this condition, we will get our answer. It is as simple as that. Modified condition. This is also modified condition. Modified, or we can say the extra condition. Let's run the code. Let's submit the code. Yes, all test cases are submitted. Its time complexity is big of log n. Space is big of 1, because using the binary search, no space is used. Thanks for watching.